So, jetzt geht's los. Good day everyone, welcome back to my lecture on mechanical behavior of materials, course number 315008. I'm Klaus-Dieter and we are writing the spring semester 2022. Let's get into the Weibull statistics. The Weibull statistics is an approach for statistical description of when a material fails or not, which is particularly useful for the brittle materials because they may have a statistical broad distribution on failure or not. Here's some of the literature. Marc-André Meyers and Christian Kumar-Karla, Mechanical Behavior of Materials at the Cambridge University Press. So what we treat in this lesson is the strength distribution of a brittle and ductile or any material and the distribution function of when the material fails, at what stress. So we see for brittle material we have a broad distribution, while for ductile material the distribution is narrow. That means it's more predictable. The Weibull statistics is applied primarily to the strength of brittle materials, since the strengths of these materials are not deterministic. Hence, we define the failure of survival probability. The reason is as follows. The strength of a brittle material, ceramics, glasses, is well defined by this equation, which we derived one lesson ago. So sigma is the K1C, the stress intensity factor, divided by a beta constant, and square root of pi times A critical length. So A is the crack length. While K1C is well defined, the largest flow size in the specimen AC varies considerably in a set of specimens made of the same material. Also in brackets here, the variation of flow sizes in a single specimen is less important. So what does it mean? If we have a given material, let's take some window glass, it may have some inclusions, it may have some cracks, it may have some bubbles inside. And these, through the A, determine a critical stress sigma as given by this equation. So now these sizes of bubbles or inclusions, precipitates, soft precipitates in steel, like sulfides, they lead to crack stress concentration and eventually may lead to crack initiation and propagation, as we know already. So the size of these flows, they may have some distribution, and also it depends critically, or 1 over square root AC, on that crack size, flow size. So therefore, the strength distribution in a group of specimens may vary considerably. With many specimens, particularly a group of specimens from a class of materials, like say window glass, which is made by one company and by another company, and they make it slightly different. The one works a little cleaner, the other not so clean. I know there are standards, but even in these standards there are some variations, depending on the day, on the production process, on the dust which comes in, and so on. So, let's set up a model, namely the model of the chain with the weakest link. So if we consider a chain of a length L, then the chain is only as strong as its weakest link. So when we pull that chain and we have the weak link here, then it will break at the weakest link. If the strength of the links is distributed evenly, then the probability of survival of a chain with length L is defined as some probability of survival S of L, of the length L, which obviously should be smaller than 1. because if it's 1, then it's trivial, it always survives, you cannot break it. And it's smaller than 1 if you apply some stress. Then the probability of survival of a change of twice the length results in PS of 2L equals PS of the first part times PS of the second part, which is also L because we say it's 2L. So it's not a plus, it's a multiplication. The probabilities, they multiply. You know that from probability, statistical mechanics and so on. And because both halves of the chain must survive, means the PS of the 2L has to be smaller than the PS of the L. That's a condition, right? That's also a condition that PS of L is smaller than 1. If it's bigger than 1, it doesn't make sense. So here again, the model of the chain with the weakest links. We assume now a probability PF of lengths failing at sigma. And if we call that R of sigma, the probability of failing PF at sigma is R of sigma. Means the survival S, as before, is 1 minus R of sigma. And obviously with the formula we derived here, this multiplication depends on the L. Now we write it down for delta L. So the probability of failure of the length delta L for failing at sigma is R of sigma times delta L over L0. And the P survival is then 1 minus the failure. So 1 minus R of sigma times delta L over L0. So the P survival of the length L plus delta L for surviving at sigma is the piece of length L0, which is shown here, multiplies by the PS of the length of delta L. This is the multiplication we put in before. Leading to this equation, PS of L plus delta L equals PS of L0 times 1 minus this function R of sigma delta L over L. We can write down the same thoughts in 3 dimensions, where instead of an L we have a volume. So the failure may occur anywhere in the volume, not just in the linear chain, but in the volume. And I make the volume bigger, I get the multiplication of the probability which goes with the volume. So we do the same. PS of V0 plus delta V becomes PS of V0 times 1 minus R of sigma delta V over V0. And now we go to infinitesimal small delta V becomes dV. We get this differential equation here. dPS of V over dV equals minus R of sigma times PS of V over V0. This equation we can integrate. So we integrate, becoming then R of sigma times V over V0. And that follows PS is the exponential of minus R of sigma times V over V0 plus a constant C. And now, because PS equals 1 only for V equals 0, means the C has to be 0 as well, resulting here into PS is just an exponential minus R of sigma times V over V0. So we have a volume V0 to which we normalize, and we vary as a function of V here, and it goes down with the minus exponentially. That means the probability or the R sigma which is shown here. So the V0, if I vary as a function of V0, the V0 is in the denominator, then the curve is like this. And if I vary as a function of R, so I have three variables here. I have R, I have V, and I have V0. So if I hold two of them constant and one as a variable, which I put here, then I get one of these three curves. So twice I get the curve. For R, I get the curve which descends, and for V, I get the curve which descends. And obviously, for V0, because it's a denominator, it goes up. So, if the stress now varies from place to place, we said so far we have had a stress, a volume, and the stress was constant, sigma everywhere. Now, if there is a variation, then of course we have to put the integral here, integral of R of sigma, where R of sigma is the probability of V0 failing at the stress sigma, and we have to integrate dV over V0 with the local probability or with the local stress. So Weibull now proposed a simple parametric solution for the probability. It's not a physical solution, it's just a parametrization for the probability of failure R of sigma. So he said R of sigma, let's write it like this. R of sigma is sigma minus sigma c over sigma 0 to the m. So m, we have seen that many times. We describe it by a potential function. And this m we call the Weibull modulus. Sigma 0 is a characteristic strength, which is in the denominator there. And sigma c is a critical stress. If we go below this critical stress, no failure occurs. And sigma is the variable, so this is the stress at failure. What stress in an experiment we apply until it fails. So now it's possible to calculate PS for component on the mechanical stress. Namely, we have the P for survival, probability of survival, equals exponential of minus the integral R of sigma, for which we put in the sigma minus sigma c over sigma 0, times dV over V0. And that leads to, here we put it in, to that equation. And if the whole component stays under the same stress, the equation reduces, we remove the integral, and the dV over V0 becomes a V over V0. So PS equals exponential minus sigma critical over sigma 0 to the m, all in the exponent, V over V0. And the probability of failure, of course, it's 1 minus P survival. It's just 1 minus this exponential function. So if the stress below which no failure occurs is neglected, that's the sigma c, we say sigma c is 0 megapascal. That's an approximation. Let's say, okay, we just put it 0. And if the volume is normalized, let's say to a standardized test bar, then the equation reduces to this. Now the volume is normalized. The volume V is normalized. Let's make it V0. And in the standard experiment, as described by the societies ASM, so engineering standards, then PF, the probability of failure, becomes 1 minus exponential of minus sigma over sigma 0 to the m. Note, this is a pure mathematical description, and at this point doesn't have any material scientific meaning. Weibull just proposed a function which simply fits the behavior. However, the sigma 0, the m, and the sigma, they must somehow correlate with the density of the defects. They must somehow correlate to the material, not just these mathematical thoughts. So we have an equation, and now we need to look into it, what it means. So if we write again here the PF equals 1 minus exponential to the minus sigma over sigma 0 to the m. I said already we have the Weibull module m describing the failure probability curve, and here to the right I have plotted for you a few of those curves with the stress to the critical stress ratio, so sigma over sigma 0, and the probability of failure, this PF. For different m. So the m's, they are listed here to the right. And what we see, if m equals 0, then we just get a constant. M equals 0 is e to the minus 1. 1 minus e to the minus 1 is something 60%, roughly. You can work it out. If m equals 1, then we have a pure exponential, right? So m equals 1 is the black line here. It's just the exponential which goes up. If the stress is higher, the probability of failure exponentially goes up with asymptotic to 1. If I make the stress very high, I have 100% of failure. Or very close, 100% of failure. Asymptotic to 1. Right, so we can understand that. This is shown here in that graph as well. Now, if we make m very large, let's say we make m larger, so m equals 2 is the pink curve here. We see it increases, m equals 4 becomes this red curve, and m equals 1000 becomes this very steep curve. So it looks more like it resembles a little bit to the error function. It's not exactly the error function, but it resembles to the error function. Means it goes up in this way. And how it goes up, the width of going up depends on the Weibull module m, so on the exponent m in the exponent of the exponential function. So the m describes somehow the width when it goes the full width half maximum. If it goes from here to here, then this is the width, yeah? From one level, let's say below 0.2 and above 0.8, so you exclude that, and you look to the full width half maximum, or to the width in the stress range. So you see already it's something 1 over m, the width. And as m becomes smaller, as m becomes larger, the width becomes smaller. We're not looking too much into exponents smaller than 1. So if PF becomes infinity, then we can say the PF is 0 if sigma is smaller than sigma 0. We see that here. This is 1, yeah. And it becomes 1 if sigma is larger than sigma 0. We can see that from the graph here. So for large M, we have the narrow distribution and a small spread. That means the material is reliable. It falls somewhere in this range. It's reliable. For small m, we have a wide distribution, so it can fail here, but also can only fail at way higher stresses. So this is hard to predict. It's an unreliable material. So these are four bad ceramic components, bad in a way looking to fracture. The M is 1 to 10. And for tough ceramic components, it's 10 to 40. And for metals, it goes to 100. 100 I haven't shown here, but this is maybe something like that. So let's calculate M and sigma 0. So first, we define the test volume, e.g. a test bar, according to the standards when you do the fracture testing. We have our function here. And then we make a graph with the left term on the y-axis. So we rearrange first this equation and take twice the logarithm. So we put the 1 on the other side, yeah, gives the 1 minus pf. Then we turn it over, 1 over, to get rid of the minus here. And get twice the logarithm. Then we get ln of ln 1 over 1 minus pf equals m, this exponent, times ln sigma, minus m times ln sigma 0. So we can write down this as a linear equation, parameters y is all that, times equals m times x plus c. So in this coordinate system where we plot the ln of ln 1 over 1 minus pf versus ln sigma here, we get the slope m, so we get the Weibull modulus m. And we get the stress sigma 0. This is the axis offset in this graph. So we make the graph with the left term on the y-axis and the right term as the x-axis and insert the measured values. So you would make experiments and get values here. Yeah, get values and then you fit the straight line. You do the experiments by applying a stress S, in this case should be sigma, on specimens having the same area A and the length L. Manufactured by same processing route and have same properties, and surface roughness will result with strength distribution. So make them all the same. And this distribution is low for metals and high for ceramics. That's what I say already. The distribution of failure. Therefore, the strength of the materials with high distribution can no longer be defined by a single parameter, the strength, but also needs to consider the distribution or the survival probability P. P is F of sigma. For low stress, P equals 1, and for high stress, P equals 0. Namely, the survival probability of failure is 0% for high stress. So what does it mean? Here we put the sigma and we put the survival probability P here. It's 1 for small stresses and it goes to 0 for very high stresses, and then it goes down by this arrow-like function. And if I look now to two specimens, I look to the specimens 1, which has a single volume, and apply the stress sigma. So it has an area A and a length L. So for 1 I get this curve. For specimens A times L, we get, let's say, 50%. I look to that point here of the specimen surface below, and 50% fail above sigma 1. So this is my sigma 1. And the point 2 is if I take 2 specimens, as shown here and there, in parallel or in series, then the probability at stress sigma 1, the probability is 0.5 times 0.5, so it becomes 0.25. And in this model, it doesn't matter whether you put them in parallel or in series, because here you may have cracks. If you have a crack there, then the whole thing fails. And here as well, if you have a crack just in one, the whole thing fails. And if you have a crack in another one, and you have a crack in another one, also the whole thing fails. So it doesn't matter. It just goes with the volume, but not on the position of the volume. So now let's define the probability of rupture. S. S equals 1 minus P. And then, of course, we get the inversion of this curve, 1 minus, yeah. Probability of rupture, let's say at sigma 1, I get the point 1 here. And at sigma 2, well, I have to take this point 2 minus the point 2, which was 25%, so I get 75%, 0.75 for the probability of rupture. So if S is the failure probability of specimen of unique length L for small n L specimens L, then 1 minus SL equals 1 minus S to the L. So I have a small length. And I now can take the logarithm. Logarithm 1 minus SL equals L times log 1 minus S. And the same we can write down for the volume. So we can argue with L, or we can argue with the volume. I'm sorry, these slides, they're not very consistent. Before we had S for survival, now S is for failure here. But that's how it goes at Technion. So now let's define a risk or rupture parameter B. So this log of 1 minus SV, which we introduced here, we call B. And this is minus V times log 1 minus S. And it has a negative sign because 1 minus S is smaller than 1. And we can take the differential now. So the dB equals minus log 1 minus S dV, or dB equals, now we call this minus log of 1 minus S, we call that an n of sigma times dV. But the probability for survival P and for failure S is a function f of sigma. Not the same function, but the function f of sigma. The one is 1 minus the other. Let's integrate it. So B becomes now integrate over the volume n of sigma times dV, or since B is that, then we get S equals 1 minus e to the minus b equals 1 minus e to the minus the integral of n of sigma dV. So the risk of rupture depends on the stresses in the volume V. And of course, yeah, and it depends on the stress distribution of the stresses in V. So volume is applied, assuming the rupture initiates in the volume. And if the rupture initiates along the surface, then we put the surface in. So we integrate over the surface A. So it depends on the model where the stress initiates, the failure initiates. If it initiates in the volume by inclusions, then we put the volume in. If we say there's no nucleation of cracks within the volume, but only at the surfaces, surface roughness and so, then we integrate over the surface. So it's a slight modification of the formula, but the formalism behind is the same. And now again, always do the same. We say now n of sigma is a potential function of sigma again with a constant k. And k, let's say k is 1 over sigma 0 to the m. So for specimens having the volume V is unity, all specimens have the same volume, means it, then the failure probability is 1 minus e to the minus sigma of the sigma 0 to the m. So we have two parameters in the Weibull statistics. We have the sigma 0, which is the mean or median stress, and we have the Weibull modulus m. We have seen that before, right? For unity, volume and sigma equals sigma 0, then the S becomes 0.63. Yeah, that becomes then 1, e to the minus 1 to the m is e to the minus 1. 1 minus e to the minus 1 is 0.63. So this is the median stress. And in the curves which I've calculated already, you see at 1 they all cross at 0.63 or 63%. For the uniform stress distribution in the specimen, we get now B equals this integral over the volume. We have had that n of sigma, so it's stress distribution dV. And we put that in, n of sigma here from the top, k times sigma to the m dV, and that we can solve equals k times v sigma to the m equals v times sigma over sigma 0 together to the m. On the other hand, sigma is a function of xyz times some normalizing stress, sigma p. Let's say sigma p can be the maximal applied stress in your experiment. And then the sigma in the whole sample is a function times that stress. Can be higher, stress concentration can be lower in other regions of the material. So hence, the B becomes this integral now over sigma p times this function dV, and this function we can calculate already. For example, we have had the bent beam with two momentum torques at the ends, otherwise free. So we can look up the sigma. We have done that in the theory of elasticity, and it works out sigma is sigma p y over h. We see here's the coordinate system, y is the vertical, and h, 2h is the height of that beam. So the stress is sigma p times y over h. And now sigma to the m equals sigma p to the m y over h to the m. And we can integrate that, but we only integrate it only over half the thickness. So the thickness from here to the bottom, if if this is the tensile region, because in the compressive region we would not have crack initiation, we have closure of cracks. So the material only fails if the crack opens. So this was the sigma critical which I introduced and then put to 0. So if I'm smaller than that sigma critical, then nothing happens. The cracks would close in this way. So we integrate only half the thickness, namely that one which is under tension, and get this formula here. It looks a little bit complicated. Now you're better at mathematics than I, so I let you do that. So B, again, is this function, and we can write it down now, K sigma P to the M, V over 2M plus 1. If now the same specimen, but under pure tension, not the bending, but pure tension, we would get another B, which would be V times K sigma to the M over P. So we have K sigma to the M times V, we see that here in the top formula, divided by P, see that here as well. But here, with the bending, we have the decoration of 1 over 2M plus 1. So to compare between the two cases, the risk of rupture of the bending and the pure tensile experiment, let's say this probability of failure we put equal, then it works out the sigma bending divided by sigma tension scales by the factor 2 m plus 1 to the 1 over m. So this is very important. Due to different stress distributions, the failure stress for the same risk of rupture B, is different and depends upon m. Yeah? It depends on m. If m is very large, 1 over m goes to 0, then that goes to 1. If m is small, if m equals 1, let's say, then we have 2, 3, 4, then sigma bending would be 4 times as strong, or can be 4 times as high as for tension. So for m equals 100, the sigma b over sigma t is 1.05. That's what I say. If m becomes large, it goes to 1. This is for metals. And if m is 3, I just said it for 1. So if m equals 3, then sigma b over sigma t becomes 2. That means in the bending stress can be twice larger than the tensile stress, or in the tensile loading experiment or situation, application in the airplane. And we can integrate that over x and y. So sigma 3 pure bending and sigma tension becomes this formula here. Same formula. So for m equals 3, then sigma 3 probability over sigma bending is 3.17. So I can make the stresses 3 times higher than in the pure tensile experiment. What I want to say, it depends very much on the geometry of the loading. Here are typical values for m. Just repeat what I said before. For metals, the m is around 100 and the curve looks like this. So this is the probability of survival now. of failure, which is 0, no failure at low stresses, and failure if you go above this value, sigma 0. For ceramics, it's 5 to 20. So if this is sigma 0, or sigma 0 is a 63% here, then we get this distribution. So here we can go in our design close to sigma 0. Here we have to be quite a bit away, maybe half sigma 0. You have to work it out, the probability of failure you want to have, yeah? And for composites, it's 2 to 4. Also for brick and chalk and so. So that's why you don't build an airplane out of brick or chalk. See, here's a 63%, so this would be our sigma 0. And you cannot go close to sigma 0. Even half at sigma 0, you still have some relative high probability of failure, which you do not want to have in a high engineering device. So you have to design for really low stresses. Again, how to evaluate sigma 0 and m. I work through that because you will have homework, you will have tutorials on that. So we plot this ln sigma against the ln 1 over 1 minus probability of failure. So probability of failure is 1. We have had this formula e to the minus sigma over sigma 0. And here, same as before, we have the double logarithm, gives this linear function. I don't know why they repeat it here. And the minimum number of specimens, according to standardization, is you need 15 specimens minimal. And you fracture them to evaluate the failure probability of the 16th specimen. So you have these 15s. What's the probability of the next one? So get a data set for the mean stresses, and then you arrange the data set descending in order of strength. So you have serial numbers, you have failure load in Newton. You have the failure strength, so you have the load, you can calculate the strength by knowing the cross section, and then you put this function 1 minus s, 1 minus n divided by n plus 1 becomes this. These values, and then the ln sigma, the sigma is here, so ln sigma becomes those values, and you plot them. You plot them, you fit the line m, in this case becomes 4.7848, and the sigma 0 or s, they call it here, is 122, and from that you can work it out. Here, another example, another exercise, typical exercise for exam questions. A component is made of alumina with m equals 10, so it's quite brittle, and sigma 0, 200 megapascal. So the question now is, what are the allowed stresses for a survival of 99.99%? Means the probability of survival, it's not in percent, it's the fraction, 0.9999. So we write down our formula, S equals 1 minus e to the minus sigma over sigma 0 to the m. Take the logarithm here and eventually work out sigma. This is what we're interested in. Equals sigma 0 times minus ln 1 minus s to the 1 over m. So this is just worked out, that formula. rearrange the terms, take the logarithms, or take the logarithms and then rearrange them. And now we put the numbers in. So 1 minus s is 0.9999. This is the probability we want to have. The sigma 0 is 200 megapascal. And m is 10, so 1 over 10. That gives you 80 megapascal. So if I apply a stress at 80 megapascal, then the probability of failure is 0.9999. As an example, what happens if I put 80%, not 0.9999, but 0.80? So for S is 0%, 80%, then it works out to 208 megapascal. We see we can increase the stress, but then the probability of survival for 80% goes down. Well, the probability of survival, I say, okay, I can design, I make some balloons for playing with the kids, which I launch into the sky. Well, I'm happy if 80% of these balloons survive. The kids, they still have fun. But it's not critical, it's not life-threatening. However, when I design an airplane, then I want to have a probability of survival, 0.99999, many nines, before it fails. So it depends on the situation. Can you afford the failure or not? If you can afford the failure, you can put more air into the balloon, so the balloon stresses more, it's bigger, it's more fun. If you punch it with a needle, it makes a bigger bang, so more effect in a show. But probability of survival may be less, 80%. Or on the other hand, you really want to have it, you have a scientific experiment, you build a balloon, you send it up in the stratosphere, or to the moon, into the stratosphere, Then you make it conservative, because you don't want to have your experiment with a lot of load failing in half the way up. So it depends on the situation, what you allow as a probability of failure in your engineering design, and then you can calculate the probability of survival for that probability, or the stress, the maximum stress for that given probability of survival. Here also, regarding the volume effect, for a set of lab specimens of the volume V0, let's say V0 is unity volume, with sigma 0 and m, the Weibull parameters and the Weibull parameter m, we get this probability P of sigma V0 as hat. So the V0, the V equals V0, we get sigma over sigma 0 to the m. Now, if we take the same kind of specimen, the same geometry, but a larger or a different volume V, larger or smaller, then of course it scales with V over V0 in the exponent. And that is shown here. So here in the middle curve, the central curve, is for the volume V0. Now if I increase the volume, then I go down here with the probability. And that we know already, because if you have 50%, if you double the volume, then it goes down to 25%. We have said that already before. If I make the volume smaller, then I have a higher probability of survival. So evident. Just remember, if I have a V0, if I increase the volume, I go in this direction with my curve. And obviously, if I decrease the volume, I go in the other direction. This is nice to remember. I think this is really the same thing what I said before, with the same risk of rupture B. Then, or if I design with the same risk of rupture B, then the stresses sigma prime over sigma 0 scale with V0 over V to the 1 over M. So for a given risk of rupture, I shift the curves as shown here. And it scales inversely. So I have the 0 here in the denominator, I have the V in the nominator. So it scales inversely with the volume to the 1 over M. This is scaling you need to remember. Right, so I have introduced this Weibull distribution. I said again, there's a nice book, Mechanical Behavior of Materials, which resumes this. The picture I've shown at the beginning, you understand now a little better. Namely, we have the stress here on the abscissor and the probability of failure at that stress, or the number, not the probability of failure, the number of failures, number density of failures at a given stress. For the ductile material, I have a very sharp distribution. For the brittle material, I have this very broad distribution, eventually with a tail as well. And now we can make up a big, this is for a given volume, so one of these unit volumes. Now if you have a solid body with volume V composed of n cubes with volume V0 each, then we just need to multiply all the elements together. If the stress is homogeneous, so everywhere the same, then it's relatively easy. Otherwise you have to integrate over the stress distribution of the whole system. And in a realistic simulation, this can be done by finite element analysis. Weibull has introduced this distribution for the description of failure. But it is also relevant for other statistical behavior, for example in survival analysis. You go out in the wilderness and you survive or not. And if you have several people in survival, then surviving or not may depend on the other, and you can have a weak link for surviving. Or surviving of parts, yeah? Failure. When does your part survive? To represent manufacturing and delivery times in industrial engineering. So that's, or in extreme value theory, in weather forecasting, in reliability engineering and failure analysis, that's what we did. In radar systems to model the dispersion of the received signals level produced by some types of clutters. So you transmit a signal in radar and it doesn't go through, and that depends on the distance, on the volume the radar wave goes. To model fading channels in wireless communications, as the Weibull fading model seems to exhibit good fit to experimental fading channels measurement. In general insurance, to model the size of reinsurance claims and the cumulative development of asbestosis losses. In forecasting technological change, also known as the Sharif Islam model. And to describe the wind speed distributions as the natural distribution often matches the Weibull shape. So Weibull distribution in mathematics and statistical analysis became very important over many applications as demonstrated or mentioned on this page here. Not only for the engineering failure analysis, where Weibull originally has introduced it. Most of these distribution functions are not symmetric, so we have a median value, we have the mode and the mean value, so mean value. The mode value is the maximum here, mode is t mode is maximum of f of t, and the median value is where we have 50% in this area and 50% in the other tail of the curve. So not symmetric curves, and then you have to distinguish between the mode, the median, and the mean value. Here are some examples on the Weibull distribution. So there's a Weibull plot for steel, a conventional alumina, and a controlled particle size alumina. Note that the slope, which is the Weibull modulus, towards infinity for steel. So steel is here, 0.2 carbon rolled steel. For the controlled particle dispersed alumina, the M is double that of the conventional alumina. And this after that. So CPS conventional alumina, we have a relatively low slope, and the slope becomes steeper for the controlled particle size. That means all the particles, they have the same size. Alumina, you know, it's a polycrystalline material. It's made by crystallites. They are sintered together, or they're ground together. And if you have a controlled particle size distribution, let's say all the same, then you have better statistics in failure. So a higher M is 9.7 here, then as compared to just a very dispersed particle size with a broad distribution. Because if you have a broad distribution of particle size, you also have a broad distribution of flaws and imperfections. So this is a nice example how you can design the Weibull modulus M by controlling the microstructure of the material. Or here at the bottom, what we have there, cumulative probability of flexural strength, 4-point bend test with inner for 3 ceramics. So we have 3 ceramics, aluminium nitride, silicon carbide, and silicon nitride. And we see aluminium nitride has a very steep curve here. That means the M is large and it's relatively predictable. So that means the sigma critical is somewhere here, 60%, yeah. And it's relatively predictable. You see it starts here at 175, not at 0. Silicon carbide also is relatively steep. If we look to silicon nitride, it's less steep, so it has a larger distribution. However, of course, the sigma zeros is different for the 3 types of materials. These are direct material properties. Also, what this shows, the data, they fit well the Weibull distribution. In the 2 cases, aluminum nitride, silicon carbide. In silicon nitride, it fits very well up to here, probability of failure 80%, and then it deviates a bit. So that's probably either the statistics is not good enough or the model may need to have some modification due to properties of the materials. We did many assumptions. Again, same thing, let's shorten it. Traditional ceramics, the M is smaller or equal to 3. brick, pottery, chalk. Then the engineering ceramics, it's 5 to 10. We had some of the engineering ceramics on the previous slides. And for metals, you want to have something 90 to 100. With this, I like you to digest the WeibullStatistics. It's not difficult. There's a formula we have derived. Please be aware of the formulas. Now some of the background and the applications. When I give you the probability of failure, what is the stress you can apply. Thank you very much and see you next time. Over, out.